Well, this is a fun topic. So when Stefan asked me to speak, I thought, well, gee, what can I talk about? And I decided I'll talk about what I really like the most, and that is, virtual musical instruments. I'm an instrument maker. I see myself as a digital luthier. And when everything settles down and I've got time to work, I go off and I chip away at my bits and come up with new sounds, new instruments. And so that's what I'm going to talk about, but I'm going to talk about it from the beginning. So I think it's enriching to see how we got where we are and how these ideas evolved. And so, as you may recall from 2006, I actually gave a very similar, I didn't realize how similar it was until I looked at it, but I did the same thing in 2006 at Lake Como, and maybe some of you were there. And so that talk was on digital audio synthesis and effects based on physical models. So not so much emphasis on history, but ended up having a pretty large history section. And so starting out with the maybe what might be the first delay effects, and then working up through waveguide models and commuted synthesis and so on. So what I did was I copied that over to a new directory, and I just started adding stuff. So today's talk is a superset of that in some sense, and also I imported some other stuff, but I'm going to really focus on all the new stuff. And the good news is I do have more than enough new stuff, but the other stuff is there, and we can drill down with questions, or you can kind of look at it later. So, so here's the overview. We start out with virtual instruments and effects. What are they? What do we mean by this? And then an overview of physical modeling. What are the various approaches that people use? And then dive into some history. And so, where did it begin? And so I'm actually going to go all the way back to Newton, and Newton's system of the world is sort of where we begin, and just kind of follow it forward from there. And then I don't have time to cover all the types of instruments, but my own first love is strings. I'm a string player myself, and I love strings. I think they're just incredibly underutilized even today. And the connection between strings and voice is very deep. So it's good to kind of see them both at the same time. The vibrating string and the acoustic tube essentially have the same model. And so we'll look at the history of some of that, and just really some updates, and then some selected research updates, and that's all we have time for. So jumping in, what do we mean when we say we want to virtualize something, or what is a virtual anything? Well, I looked it up, and according to Merriam-Webster, it's being on or simulated on a computer or computer network. So you have print books and you have virtual books. And it's also a virtual something if it exists within a virtual reality. And so virtual reality is a big thing nowadays. It's getting bigger all the time. And according to Elon Musk, we may be living in virtual reality right now. He says there's a 1 billion to 1 chance that we're living in base reality. And I don't know exactly how he calculates that, but that's very, very interesting. So we have to be careful here. So, it could be virtual all the way down, not turtles, virtual. And virtual turtles, and then we can say then that virtualization involves one level of simulation. So if you just back up one, we can say it's a virtual something. And so I have an example from my childhood. One of the things I used to play with was a duck call. Mine looked like this, but I found this one on the web, which is much more snazzy. Might even work better, who knows? And so a duck call is a virtual quacking device. So you call ducks with it. It makes you sound like a duck, all right? And so if we synthesize this, which is probably going to show up someday, somebody will do it, then you've got a virtual quacker device. And so I'm even proposing a notation, V squared, a V squared quacker. So, we can try to keep track of our layers of virtualization. But I'm just going to talk about one layer of virtualization. That's basically going from just the physical world to mathematical models. That's a virtualization right there. F equals MA is a first step in virtualization, getting mathematical descriptions. So we're going to follow Isaac Newton's system of the world. We don't need relativity. We don't need quantum mechanics, really, although you sort of do sometimes for gases. And so we can really just get by with this one, F equals ma. The vector force is equal to the mass times the acceleration, which is a vector. And I like to think of it, I guess, everyone likes to think of it as an expression of conservation of momentum. So momentum is typically denoted P, and so for a moving mass, it's the mass times the velocity. And so what we're saying really is that if you're going to change the momentum, P dot is the time derivative of momentum, then you're going to need an external force. So forces cause changes in momentum. If you don't have a force, an external force, then you can't change momentum. Momentum is conserved. And it's interesting in the relativistic formulation of this stuff, there's this idea of 4 momentum, which is interesting in the 4-dimensional space-time. And the 0th component of that is energy. So conservation of energy is just a byproduct of conservation of momentum. And it's much more unified in that formulation. So that's the equation that we can get a lot of mileage out of in creating virtual instruments. However, it does get very complicated very quickly, and so we have various approximation techniques. And so what keeps us busy year after year is finding really efficient but high quality approximations to the complete model. But we want to preserve sound quality and the expressivity of control. We don't want to give up any control dimensions. We have to be able to express fluidly through the virtual instrument as if it were a real instrument. So what do we do when we do physical modeling? Well, we usually start with a differential equation. So F equals ma is a differential equation. And it's called an ordinary differential equation. It's just a time derivative, ODE. And then we can introduce a spatial dimension and have a partial differential equation. And that's what we need for the vibrating string and the acoustic tube. And then when we go to the computer, we have to discretize these things. So we'll sample the time axis, we'll sample the spatial axes, and get some form of difference equation. And so here's a very simple discretization of momentum at time n plus 1 is the previous momentum plus the sampling interval times the force applied through that time interval, which is assumed constant over the sample. That's a very, very simple difference equation corresponding to the differential equation, the ODE of the F equals ma. And then there's a much larger set of tools, other forms of difference equations that we call finite difference schemes, and they may have various properties and various convergence and stability properties and so on, and you've seen some of those yesterday. And so we also may organize our calculations into state space models, and you saw that in Dave Berner's talk, the state space formulation. And you can think of that as a vector first order ODE. So it's just collecting the computations together. And in researching for this talk, I discovered that Lagrange actually did that for the vibrating string in the 1700s and diagonalized it and got the modes of the string. And that led him to essentially eigenfunctions of Hermitian operators and projecting onto them. So the vibrating string actually launched all that stuff as well. So you can also organize things as transfer functions. And so this sort of gets us in the direction of signal processing. But in physical modeling, of course, we'll have known units for our signals, and we may have units for our transfer functions. So if it's force over velocity, then it's an impedance, or it may be an admittance. And so we think of these as physical black boxes, not just black boxes. We don't abstract away the physics, but we still work with transfer functions. And then for implementation, we very often will expand our transfer functions into parallel banks of biquads. They have good numerical properties, biquads being second order transfer functions. And we like to draw equivalent circuits. So in musical acoustics, you see equivalent circuits for virtually everything that's studied. The violin is a circuit by Schelling is a classic example of that. And it's just a nice representation of the understanding of the interaction of the various elements of the physical system. And then we will take that equivalent circuit and abstract it away into an impedance network, let's say, that we want to then realize. You can then realize transfer functions using what's called network synthesis. That's a very, very large topic. A classical topic sort of led to filter design as we know it. And then a special case of finite difference schemes that is rooted in physics is wave digital filters. And so I know many of you know a lot about that. It's a network of masses and either a mass or inductor or a spring or a capacitor. In other words, mass spring systems or inductor capacitor systems. And it's a very nice paradigm that competes with things like nodal analysis. So the wave digital filter uses wave variables and then if you're not in the wave digital domain, you're probably in the Kirchhoff domain where you're using currents and voltages, and so you have those alternative choices, and they have different properties. And then if you have a string or an acoustic tube, then it's nice to jump to a propagating wave model. And so the digital waveguide method is based on that. It's sampled traveling waves with losses and dispersion implemented. And so that's our toolbox. And now I want to get into some history. My first history overhead is from Stefan Bilbao's book. Here's the book. I'm sure you're quite familiar. And so it is a nice timeline of history starting around 1950. And so this is all the kind of stuff we're doing now. And so you see that I mentioned most of this stuff. FM synthesis sort of stands out by itself. It's not really a physical model, or I think of it as a spectral model because you're matching spectra with FM groups. That's the way John Chowning really did use it, and probably still does. And then additive synthesis and modal synthesis, I claim to be talking about today. I'm going to talk about the origins of those things. And functional transformation method is related as well. It started as a kind of a bilinear transform approach to modal synthesis, as I recall, and it's gone through lots of changes. And then wave-digital synthesis goes all the way back. That was our first computer music table format, synthesis format, and we were doing triangle waves. I think Music 1 used triangle waves, if I'm not mistaken. And somebody was remarking on having heard that demo at Bell Labs and thinking to himself, I think you better get busy on Music 2. Music from triangle waves was a bit limited, but it was very powerful in the telharmonium for giving a demo of Adagio for strings by Barber, and it attracted a lot of investment and got the telharmonium built, something that took 3 train cars to transport around. That was music over the telephone lines. That was the vision of that. The telephone was very new, and so the telharmonium was this vision of being able to distribute music over the telephone. And I won't tell you how the story ends because it's a fascinating story. You should go read it up. It's an amazing story. So, and here we have, so that's wavetable, which I will not talk about. That's the only thing I'm not going to really talk about the origins of, because that's basically sampling the acoustic pressure wave. And so you could say that's a physical model. You're recording physical pressure over time. But that one's sort of considered too easy, right? So, and not as expressive as we would like. It's not sufficiently expressive. So now we'll have, growing out of speech synthesis, we have string models, the waveguide technique, hybrid techniques with other, we like to hook up waveguides to wave digital filters because they're both using traveling waves and they interface nicely. And so, but the beginning, in 1950, the only thing that really kind of made it out of the era that I'm going to talk about is the finite difference schemes. Okay, so you're taking your differential equations and you're differentiating, discretizing them, making them discrete time. And so you have your finite difference schemes in the beginning. And there was some very early application of that to music synthesis with Pierre Ruiz and Lohan Hiller. They did bowed string simulation based on finite differences. And that goes way back. And Claude Cadeaux and Antoine Chen. So you see all these things happening. And so I will definitely be talking about the history that led to this, but I also claim these things over here as well, as having the historical roots that I'm going to cover. So now I should cover finite differences because that's an important technology for virtual instruments, right? But I don't have time, and I'll refer you to the book. So that's really, thanks to Stefan, I don't have to talk about it. That's really kind of great, actually. So, so now I'll just give you a quick update on wave digital filters. This is a finite difference scheme based on the wave scattering formulation, which goes back at least to Belovitch, as far as I know. Belovitch's thesis was on a wave scattering approach to circuit theory and analysis, and that directly inspired Fetweiss to come up with wave digital filters. And so I just want to recap what you probably already know from last year or the year before, and that is that wave digital filters have now been fully generalized. They used to be restricted to parallel series connections, and there used to be only one nonlinearity allowed, which you would put at the root of a binary connection tree. And that's because these nonlinearities, they reflect. You can't stop them from reflecting. Everything else can be made reflection-free on the current sample. So you make a tree, and you propagate down the tree, and then load all your delay elements. In the next sample, you feed all that up, bounce off the root, and go back down. And that's your wave digital filter architecture. So now it's wide open. So you can have any topology, not just parallel and series. And you get these things called R nodes, which solve the general circuit topology. And you can also have any number of nonlinear elements. So you can have a vector of nonlinearities, and they'll typically interface through an R node to the rest of the wave digital filter. And so for, to remind you about that, take a look at Kurt Warner's thesis and his recent DAFx papers and other DAFx papers. It's been really covered. This has been the home of this topic, I would say. DAFx has been the home of the wave digital filter story, above all other conferences in general. And so we're still working on things like nonlinear Newton solvers and finding ways to guarantee convergence and to speed up convergence and to converge in real time. You want to do these things in real time, so you want to be able to converge adequately in, let's say, 3 iterations or 5 iterations and be able to run with it in real time. Get what's called a semi-explicit method out of an implicit method. So that's your update. And then here's the figure from Ross Dunkel's basement. He's a very passionate guitar player and wave digital filter maker, and he presented this last year at DAFx. And notice this R node. See, this is a 25-port R node. And so this is an area for research. So you see 4 tubes up at the top. They're nonlinear, so they've got to be at the root. And then you see normal wave digital filter elements. So here's your symbol for parallel combination, series combination. So this is your normal wave digital filter, just parallel series combinations of conventional elements. And this is all linear time invariant, so it all just propagates smoothly without any iteration. And your iteration is up here, solving the nonlinear the nonlinear tube curves against the hyperplane, harkening back to yesterday's talk by Dave Berner's, the hyperplane defined by the rest of the network through the R node. So that's a nice thing that we can keep working on. All right, so back to history. So I'm now going to go way back here. Okay, I'm going to go back to Newton and then bring us forward. So I call it early virtualization of strings. And they were really working hard on the string. That was a very important problem. Oh, I do have a marker there. That's interesting. At Karma, I don't. At Karma, the little hand doesn't project, so I have to use this guy, the laser. So the vibrating string was a really important object of study. In fact, it's so important that Lagrange got actually literally physically sick from it toward the end of his career. He talked about violent revulsion when anybody brought up the vibrating string. But for decades, he hung in there and made many contributions, which I will not really get to. So I'm going to focus on the period before Lagrange. He stepped in and made a lot of advances. I guess I mentioned him along the way. But we're going to really start with Newton. And in 100 years after Newton, well, almost, 1747 is when the first wave equation came out of Newton's, F equals ma. The wave equation is just F equals ma on a microscopic scale for the string. And so D'Alembert did that, and so that was the first PDE. And he also solved it to get traveling waves. And then I think, based on my reading leading up to this talk, I think that because we hear through a spectrum analyzer, and because musicians knew how to play harmonics on strings, I think we actually just could tell that there were many overtones in a string. And so there was a lot of work to reconcile that. So the first mathematical solution was traveling wave on the string. But everybody knew that it was, a sum of overtones. And so there was like 100 years of argument about it, really. And it culminated in Fourier theory. So the final resolution of the whole thing was Fourier theory, where we now know that you can make a propagating wave out of a sum of standing waves. You really can do it. It may have a little dust, but it'll be measure 0, and you can forget about it. It won't affect your inverse transform. So this was really the first Fourier series expansions were happening here. They didn't know they were Fourier series expansions. They didn't know they were complete. They didn't even believe them. They thought they weren't real. They didn't approach reasonable limits, that you couldn't do triangles with them. There was a lot of interesting stimulation by the string here. And also the concept of superposition. I think that may have also grown out of our hearing. You could hear these overtones in superposition, and so that led Bernoulli and others to think in terms of a superposition of vibrating modes, sonorous bodies with vibrating, superposition of vibrating patches. And my favorite reference on this stuff is Olivier Derigal, The Acoustic Origins of Harmonic Analysis. And so most of my quotes are just copy-pasted out of his article in the Archive for History of the Exact Sciences. And it's a very nice account. And so the first quote is Marie Mersenne on audible overtones. So this is back in 1636. This is I think about 50 years before Newton's system of the world came out. So he says, since a vibrating string produces 5 or 6 tones, everybody knows, right? The lyre goes back to 3000 BC, and every musician knows this, right? So you can hear 5 or 6 tones. It seems it is entirely necessary that it beat the air 5, 4, 3, and 2 times at the same time. And I should mention that the theory of sound at the time was purely time domain. There was no frequency domain, period. And so a pitch was a repetition rate. And the pulse shape didn't really matter. You know, it could be rounded, it could be triangular, you know, it's just some pulse, you know, that comes out at 440 beats per second, and you'll get a nice A440 out of it. And people weren't concerned about harmonics. They didn't know about harmonics. Nobody knew there was such a thing as a harmonic. The term harmonic had not been invented. I'm going to cover that. So the way harmony worked is that you would just have consonant beating. So if you sing the octave, then you've got a pulse in between every pair of pulses of the lower octave, and so that's sonorous. You know, they're beating together. And the same thing with the fifth and the third and so on. You're just getting, you know, a lot of the beats line up, and we like that. It's a consonance that comes from coincident beating, but it's purely a time domain thinking. And so, continuing his quote, so you know, the string's got to be doing this, right? We're getting these overtones, so it's got to be beating at those frequencies. So how does that work? It runs against experience. Experience clearly shows that all parts of the string make the same number of returns in the same time, because the continuous string has a single motion, even though parts near the bridge move more slowly. And so, and that is what you see. Let's see if I can get this video to launch. Let's do the local copy. And I do not know what's going to happen here. I do know that it should work. Okay, so this question will be one time, and here it is. Good. So this is a video of the plucked string, you know, high-speed photography, and they were able to see things like this to some extent. You know, you could tune it way, way down and actually see it pretty well. And you could do the vibration microscope goes way back. I'm not sure exactly how far back. So you see that. How is the string beating more than the fundamental? You know, if you look at any point of the string, it's just going at the fundamental. The whole thing moves together. And that really gave people a hard time trying to figure out how that works. And that Euler did these experiments and had the same observation and couldn't get his head around it. D'Alembert, Taylor got wedged on this. Nobody could see overtones, and neither can I. I mean, where are they, right? You don't see them. So it was a very interesting time to figure things out. Okay, so there was no notion of spectrum, and the fundamental frequency was just the periodic repetition weight. So you look at that motion and you think fundamental only. And Taylor concluded that it was fundamental only, and we'll get to Taylor, the same Taylor of Taylor series shortly. But first, you know, continuing, here's the guy who invented harmonics and nodes, so we want to hear his quote. Sauveur said in 1701, now this was after F equals ma, but before it was applied to anything in this domain. While meditating on the phenomena of sound, I was made to observe that especially at night, one may hear from long, I mean, science is not in a straight line. You know, you get these observations, and You get wedged and you get unwedged. And Aristotle wedged us for 1,000 years on the idea that motion required a continuous force. It took 1,000 years to throw that off. This one is not so bad. So we hear the other small sounds, the 12th, the 17th. I concluded that the string, in addition to undulations it makes on its entire length to form the fundamental, may divide itself in 2, 3, 4, etc. Undulations would form the octave, the 12th, the 15th. So you hear it, you know it's there, but you can't see it. So here's what they look like if you can excite them. And he did do that. So he was enough of a musician to be able to play harmonics. He was able to put a light obstacle on the string and create nodes, and they were at the integer subdivisions that you would expect. And he was surprised that the string did not move. So he would excite the string, and there were these stationary points that did not move, and it surprised him. It was not at all what you see in a pluck string. And so he called them nodes. He coined the word node, and it was inspired by the lunar nodes in the orbit of the moon, and those are where the moon's orbit crosses the sun's apparent orbit on the celestial sphere. And so your eclipses can only occur at the two lunar nodes, the intersection of those things. And so that's where our term node came from. And he also coined the term harmonic because these harmonics are harmonious with the fundamental. So harmonics and nodes, thank you, Soviet, nice terms. And now we get to Taylor, who is best known for Taylor series expansions. He also was the first to derive the fundamental frequency from fundamental constants such as the length L of the string, the tension K, and the mass density epsilon. And that was a big result. He also derived a really important result, which is that the restoring force in the string is proportional to the curvature of the string. But then he made a wrong turn. He approximated this by the distance of the string from its rest axis, being proportional to that. And the reason was he just assumed it was a sinusoid. He concluded that the sinusoidal shape was the only thing. You watch it, you see what it does, and you see that it just vibrates like a mass spring thing. It's just there's just this one mode, and after a very short time, it's very sinusoidal. So clearly, there's just one mode of vibration there, and it's a sinusoidal mode of vibration. And you make that assumption, and then you start making approximations based on that assumption, and next thing you know, you're down the wrong path. And Wallace had described the higher modes previously and didn't help. So Taylor thought that while you can have all these different initial shapes, you can deform it and let go. It would quickly assume a sinusoidal motion. And in modern terms, we would say all other motion would be evanescent. If it doesn't land on a standing wave, it doesn't land on a mode, it's just some transient thing, it's on its way out. And so he thought everything but the fundamental was evanescent. And that's what it looked like. So then Rameau was a composer, and he was interested in studying harmonic overtones toward a more scientific foundation for music theory. And this looks like the beginning of computer music to me. This is when composers are starting to get together with scientists and figuring things out. The 18th century was a wonderful time for science, and the arts and the sciences were getting together. And it just feels like a computer music collaboration between Rameau and D'Alembert. But in those days, the great complement for a mathematician and scientist was geometer. Even though geometry was basically obsolete, they called each other in print. They called each other great geometers if they wanted to really complement each other. And so this would be composers and geometer music, I don't know, not computer music. So it was, mathematical theories. So he based a theory of harmony on the first three audible harmonics, and he knew about Sevier and Mersenne, and he cited them. He collaborated extensively with D'Alembert. They were friends and worked together over many years. And he even had a kind of place theory of hearing, which is based on the idea that the hair cells of the ear are resonating like little tuning forks. So what has been said of sonorous body. So a sonorous body is a body that has multiple overtones coming out, not necessarily harmonic, but the radiating pure tones coming out of a vibrating body, or the sonorous bodies coming from sonorous bodies. So what has been said of these separately vibrating modes of the sonorous bodies should be applied equally well to the fibers which carpet the bottom of the ears, cochlea. So we had the anatomy. We learned from our bus tour that there was grave robbing going on so that surgeons could take them apart and find out that there are hair cells in the ear. And so these fibers are so many sonorous bodies, right, to which the air transmits its vibrations and from which the perception of sounds and harmony is carried to the soul. That's the circuit. So remote regarded hair cells as banks of sympathetic resonators, and place theory of hearing went back even before him, all the way back to 1605, but it's generally credited to Helmholtz in 1857, the spectrum analysis description of hearing, but the cruder place theories go way back to 1605. Okay, enter the Bernoullis. So Johann Bernoulli was Bernoulli Sr., and he studied the mass-loaded ideal massless string. You can call it the beaded string, you know, masses interspersed by little spring segments. And so you don't need a partial differential equation. So we had ODEs, but not PDEs in 1727. F equals ma came out in 1600s, and the first PDE was D'Alembert 20 years after this. So he followed Taylor down the wrong path and assumed that the restoring force was proportional to the distance from the rest axis. And he therefore overlooked the higher modes of vibration, considering only the fundamental. But his son, Daniel, in the usual trajectory of breaking ranks with the father, was able to do that. So the father-son rebellion is able to do better than the 1,000 years of Aristotle. Just got it fixed right away. He studied the vertically suspended chain and saw not only superposition of modes, but also that they were not harmonic, so that a vibrating one-dimensional thing could give you inharmonic modes of vibration. And when he had discrete masses, he found that he could make as many modes as he had masses. He also found the limiting mode shapes, which we now call Bessel functions. And he realized that the infinitely long chain could be used as a model for an infinitely long vibrating string. And so he realized the connection there and did experiments and really saw these things and heard them and had a very strong intuition. And a lot of what he says seems to be driven from this intimate intuition that he developed. And so in elastic bands, he is coming closer to the string. And here's what he says about these. And I think this is a really good quote because it gives a sense of his understanding of superposition, his origination really of superposition as we know it. So he says, both sounds exist at once and are very distinctly perceived. This is no wonder since neither oscillation helps or hinders the other. That's superposition. Indeed, when the band is curved by reason of one oscillation, it may always be considered as straight in respect to another oscillation, superposition. Since the oscillations are virtually infinitely small, therefore, oscillations of any kind may occur whether the band be destitute of all other oscillations or executing others at the same time. In free bands, the hanging chain thing, whose oscillations we shall now examine, I have often perceived 3 or 4 sounds at the same time. It's easier to hear them when they're not harmonic. So he clearly conceived of superposition of vibrations. And this has been a very important concept. And this was later confirmed. So it led people like D'Alembert to actually notice that in the differential equations that you have a superposition of solutions. And so there we are. So this is just kind of a wrap up of that. So string harmonic overtones were obvious to musicians. They were observed by Mersenne, Sauvier, and Bernoulli and others, but they were not obvious to everyone. So you can bet that most likely Taylor and Bernoulli Sr. and D'Alembert and Euler did not play guitar or lute or whatever was around. They tried to see it scientifically and couldn't, and we see why. So the person who really pushed this superposition of resonance was Bernoulli, Daniel Bernoulli. And then D'Alembert and Euler just couldn't deal with that because it obviously couldn't work. How are you going to add up sine waves and get a propagating pulse on the string? This is before Fourier theory, where that just seemed completely impossible. And so now we make it to D'Alembert in 1746, and he invented the PDE by plugging in Taylor's restoring force F into Newton's F equals ma, and he got the partial differential equation, and then he promptly solved it to get traveling waves. And he demonstrated that Taylor's sinusoidal fundamental was a solution, but it was a special case. You can excite just the fundamental and nothing else, but that's not all. And so he rejected Taylor's claim that only a sinusoid could be supported. He showed many more solutions. And so, but he didn't think you could do a triangular shape. So he didn't think he had them all. So the normal pluck shape, he didn't see how to do. Now Euler jumped in, saw this was a hot topic, and quickly generalized his results to any initial shape. He also allowed non-differentiable connections, piecewise continuous, piecewise differentiable functions. And then he wrote down this formula, which is very interesting. So it's the superposition of sinusoids, and if you set time to 0, you've actually got a Fourier expansion of the initial string shape. But this was before Fourier theory. He didn't know if this was a complete, there was no idea that this might be a complete description. Didn't consider it general, and it obviously could not make a triangle. You know, it was a bunch of roly-poly sine waves. You're not going to make anything with a corner. You're not going to make a propagating pulse. Anyone who flicked a rope knew that you could send a pulse on this thing, and or you could just listen to a string. You could hit it and sound would propagate at a fixed speed. So, but we now know that Fourier theory was the answer, but Fourier himself was not even born. Joseph Fourier was still unborn. We had a long way to wait. So to kind of, so then Bernoulli writes back, annoyed with D'Alembert and Euler, that he had published the superposition of sinusoids a long time ago. The supposedly new solutions of D'Alembert and Euler were simply a mixture of simple modes. Just look at that. You're just burying this stuff, this simple superposition of sonorous bodies in all this math. He didn't like using simple pure oscillations fused into a single formula, and he considered his physical analysis preferable. And here's a quote on this. Get it from him directly. I saw at once that one could admit this multitude of Taylorian sine curves only in a sense altogether improper. I do not less admire the calculations of Messieurs D'Alembert and Euler, which certainly include what is most profound and most advanced in all of analysis, but which show at the same time that an abstract analysis, if heeded without any synthetic, i.e. physical, examination of the question proposed, is more likely to surprise than to enlighten. And it's good surprise, though. It seems to me that giving attention to the nature of vibrations or strings suffices to foresee without any calculation that all these great geometers have found by the most difficult and abstract calculations that the analytic mind has yet conceived. So I think Bernoulli was a physicist at heart, and Euler was a mathematician at heart, and D'Alembert, he did everything. He invented eyeglasses. D'Alembert is also the creator of the optical glasses that we wear. Okay, so to wrap up the vibrating string puzzle, Bernoulli thought that vibration should be understood as simple modes. The string is just oscillating in a pure sinusoidal way at multiple frequencies, and these superposition. And then Euler comes up with this very general formula. This is really good. This can take you a long way. And then D'Alembert, in solving the PD, came up with the traveling wave solution. And so, but nobody thought that they were the same thing. And there was, D'Alembert thought this was the way to go, but don't write it down. Bernoulli thought this was the way to go, but don't write it out in a bunch of math. Just the superposition of resonant modes is what you're talking about. And D'Alembert and Euler knew that you could do traveling waves and that you had the infinite series case, but they didn't know what else might be out there. But we know that these can be made equivalent. You can set t equal to 0 and call this a Fourier expansion and get anything you want, including any two traveling waves. You can also pick any two you can pick a pair of left and right traveling waves to get anything you want as well. So in fact, just take any arbitrary initial shape and say half of it is going to the right and half of it is going to the left, and there you are. And then you can do a Fourier expansion of that and get the the upper equation. And the fact that the ends of the string are clamped is just a boundary condition, and that is accommodated by both Fourier theory and the reflection of the traveling waves. They just reflect with an inversion. But people were worried because how can a sum of sine waves give an arbitrary function? And so they just needed Fourier theory. So a standing wave can be, as I just said, a sum of opposite going traveling waves. And you can take any initial state and project it onto your standing wave basis functions. And so everything does work out. And I did mention this point as well. And then here's a little MATLAB for showing you how you can take any shape. In this case, just kind of the black is the initial string shape, and it's got a corner. And then what we have then are the first four sinusoidal modes. And if you do this, you have to remember to take this and reflect it with an inversion, because you need your first component to have half of a sine wave between the endpoints. And so this is so there's a DC component, then a fundamental, and then the octave, and then another, and then a fifth, and then an octave and a third. And so you have your sinusoidal expansion, and then if you add those up, if you add the first four together, you get this roly-poly approximation, and that, of course, if you keep adding the modes, you get to it with arbitrary accuracy. And Lagrange realized that. Lagrange realized that you could approach, he got to the point working with little beaded strings and laboriously calculating, he was able to show that you could get arbitrarily close to any curve with a sum of sinusoids. And so he saw the near completeness of the Fourier, the sinusoidal expansion, the sinusoidal mode expansion. So he was the first to really see that it could be done. So now some animations. Let's look at the, I think I might have this queued up. Let's see if it's there. So these are the first three modes of the hanging chain. So the fundamental is on the left, and then the first next mode. And these are Bessel functions. So it's modes 1, 2, and 3. So that was an important intuition building set of experiments that he did. And then he took that chain to infinity to address the string and then elastic bands. And then this group I basically just did with the MATLAB. And then, but this is good. Let me show you these propagating pulses. So this is two pulses propagating through each other, and by superposition they just add together. So they don't interfere with each other. So this is the Bernoullian concept of superposition, and a nice illustration of it. And then we also have this one, which is an illustration of the standing wave on the bottom expressed as a superposition of traveling waves. So the sine waves going left and right at the same speed add together to form what appears to be a standing wave. It looks like it's not going anywhere, but you don't really have to think about it that way. And an equivalent description is, you have two traveling sinusoids going in opposite directions. It's just an interference pattern, constructive, destructive, alternating. All right, so that's the history of vibrating strings. And so I have a little bit on, so the Rameau d'Alembert collaboration was a composer and geometer collaboration. And it made me think about all the collaborations I've known about. And I see a lot of them in the field of computer music. They're very common. And so I just thought I'd make a little overhead of some of the ones that I know about. It turns out that the ADSR envelope was a collaboration between the composer Herb Deutsch and Bob Moog, who was working on the Moog synthesizer. So originally the notes were just gated, just a rectangular gate. But then Deutsch was saying, you need better articulation than that. It wasn't good enough for him to just have the sinusoidal oscillator just click on, or your sawtooth just click on and click off. And so he was talking to Moog. And Moog immediately had an idea, a little RC filter, and he ran across the street and got a doorbell and hooked it up and used it to prototype it. And Deutsch and he collaborated on the ADR and ADSR They don't talk about the release to sustain. I'm not sure that came up at the same time, but at least the attack and release exponentials. Another that I've already mentioned is Laharn Hiller and Pierre Ruiz on the first finite difference schemes applied to bowed strings. And then there's an interesting one between John Lennon and Ken Townsend coming up with the flanging effect. They were not the first to do it, but they were among several, and they did it independently. And so he was working with Ken Townsend at Abbey Road Studios, and John Lennon was just tired of double tracking his vocals. You know, they would actually have to sing everything twice and then add it up to get a beefier vocal track. And so he asked Townsend, can we automate this somehow? And he came up with what he called artificial double tracking. And according to George Martin, Lennon called it flanging. So George Martin claims that that's the origin of the term flanging. And one of the ones that I saw up close was John Chowning collaborating with Dave Poole, who did the first DAFx, the digital audio converters for the Computer Music Center, the Artificial Intelligence Lab at Stanford. He took the X and Y deflection voltages of the PDP-1. It looks like an oscilloscope, and it basically is. And so you have X and Y voltages, and he brought them out to speakers. And it was basically an 8-bit stereo D to A. He also worked with Andy Moore to get a better 12-bit D to A stereo, actually quad. And that was in a big rack in the machine room. And he collaborated with Pete Sampson to get the Sampson box, which offloaded the main central time-sharing system and had this, what looked like a big green refrigerator in the machine room. It was basically a $100,000 digital hardware thing. It had ECL backplane. The backplane was about this big and had twisted pair everywhere. And it had a lot of TTL hardware plugged into it. And it did your basic, additive synthesis, subtractive synthesis. It had some reverberation, not a lot of memory, but it had a certain amount of delay memory. And you could do all the known synthesis techniques at the time, additive and FM. But it was not strong on filters. So, filter-based stuff and physical modeling stuff came enough later that it was not a great platform for that, but it was possible. You could still do it. So, and then Professor Barry Vercoe at MIT worked with Miller Puckett, who's here, and they worked on score following together. He also collaborated with Roger Dannenberg and Joe Paradiso. So, composers and geometers. Of course, Barry Vercoe did his own thing, too. I mean, he wrote C-Sound, and he's been writing it all his career. So it's been, so he's not just the composer working with the geometer, he's part composer, part geometer. I say if you can write C-Sound, you're part geometer. And so Pierre Boulez and Andrew Gerso, I watched them work extensively together, getting Répond together at IRCOM. And then I worked with David Jaffe, a composition student at Stanford. We were both graduate students, and he came to me with this Karplus-Strong algorithm and said, hey, this is cool, it kind of sounds like a guitar. But it's not in tune, and you can't do it. There's no expressive controls, and so we went round and round and back and forth, and that led to the extended Karplus-Strong. And then Paul Lansky at Princeton worked with Charles Sullivan to do the first distortion feedback guitar, and that is my next topic. Oh, but I do have a little bit of an update on voice models. I do have a little bit of time. So I got to talk a little bit about talking machines, virtual talking heads. So they used to they were made out of brass, and they called them brazen heads, these little brazen heads. So it goes back to 1125, and so there's a written description in William of Malmesbury's History of the English Kings. So Pope Sylvester II is said to have traveled to Al-Andalus and stolen a tome of secret knowledge. Sounds like Raiders of the Lost Ark. He was only able to escape through demonic assistance. This is what's written. He cast the head of a statue using his knowledge of astrology. I'm not sure how astrology helps you with busts, but his astrology helped. And it would not speak until spoken to. But then it would answer any yes-no question put to it. So there were a lot of these. And they were deemed heretical by the church and were often destroyed and were directed to be destroyed. In 1599, Albertus Magnus had a head with a human voice and breath, and it had a certain reasoning process bestowed by a cacodemon. A cacodemon is an evil demon, to be distinguished from the neutral demon and the good demon. So, you want to take its advice with a grain of salt. And then Thomas Aquinas, very well known, destroyed it because it kept interrupting his train of thought. This little cocodamon over here is driving me crazy. He destroyed it. So these things, had to do it on the down low because, the church, you could get in trouble with the church. And so, but by the 18th century, when, the period of history that I've been talking about, it was acceptable. You could say it was science. And that's what we say when we're in the memorial church popping balloons for reverberation measurement. What are you doing with that balloon? You're going to pop that balloon? We're doing science. We just, keep a straight face and call it science, and it's still fun. So here's another speaking machine, the Wolfgang von Kempelen speaking machine. It's got a bellows, it's got an articulator, and this goes back to 1791. And this is actually Joseph Faber's Euphonia, 1846, and here's another picture of it. It's got a bellows, it's got 17 levers and a telegraphic line. It could sing God Save the Queen. And it is said to have influenced Alexander Graham Bell. And you see a lot of this sort of influence, like the telharmonium influenced the Hammond organ. You can actually see in the design of the tone wheels. And then there's the ultimate speaking machine, which is the voder, demonstrated at the 1939 World's Fair. And I don't want to, I did talk about this earlier, but let me see if I can at least just play you the demo.
The machine uses only two sounds produced electrically. One of these represents the breath. The other, the vibration of the vocal cords. There are no phonograph records or anything of that sort. Only electrical circuits such as are used in telephone practice. Let's see how you put expression into a sentence. Say, she saw me, with no expression.
She saw me.
Now say it in answer to these questions. Who saw you?
She saw me.
Whom did she see?
She saw me.
Did she see you or hear you?
She saw me.
So the pitch is on a foot pedal. So you can look through these overheads and see the system here. It's a voice and unvoiced source, and you've got all these keys, and it's quite an instrument. I feel like everyone should have one in their studio. I really do. I want one. So now I get to the part that I did cover in 2006. So I will skip to the update, and the main update are these two web pages. There's one on 2D valves, and I should have them queued up in my browser. There's one, and here's the other. So so you can get links to these in the PDF. So this is amazing what you can now do in JavaScript right there in a web page. And so this is a voice synthesis tool where you can, what you have is on the horizontal axis, the first format, and then the second format. And so this harkens back to the font val diagram, F-A-N-T. Font was one of the original speech researchers, voice modeling guys. And so you can pretty well classify vowels in terms of the first two formats. Bell Labs went on to extend that to 3. Bell Labs wants at least 3 or 4 formats. That's why the telephone bandwidth is 200 to 3200 hertz to capture the first 3 or 4 formats. But you get a lot out of just the first 2. And so in this diagram, you can click on it and hear them. And the second format is most important. So you can kind of pick a nominal first format and then just march down the second format and get the beat, bit, bet, bot, boat, boot sequence. You can move through all those vowels, just moving the second format and leaving the first format alone. So that's a nice interactive tool for playing around with that. It should inspire some wah, instead of a wah pedal, why not have a weow pedal in a warrior, we were away a while ago pedal. You should be able to say a lot, and there are 2D pedals. You can get a 2D pedal on eBay. I don't know if they're being made commercially right now. So then, and then another neat new thing is called ping trombone. I don't know why it's doing. So how do I stop this for a second? Okay, let's just play it. So you see I've got a tone control. This is very innovative. Oh, I can just shut it up like this. So I don't have to destroy it like Thomas Aquinas. This one point of tongue control is very, very powerful as a controller. The pedals should follow. And you've also got a soft palate. You can open up the nasal passage and get that going. So play with that, and pardon my. I can't. I have to actually actively hold on to it. How about that? So that's pretty cool. That's really nice. I've already had 2 students pick up on it. It's all in JavaScript. I've had 2 students port it and make their own things, and everything they do sounds really good so far. So check that out. And now, okay, we've updated the voice. And then what do I have for string models? Not a lot that's new, except that to say that we're working on virtual strings now, and I have just a quick demo. But in my last couple of minutes, I'll just give you an idea of how powerful these handheld devices are now for doing this stuff in real time. and the controllers, the touch screens are incredible, and the gyros and the accelerometers. So on an iPhone 4S, which is a long ago machine, let me show you where it is on the power curve. So this is the power curve up to iPhone 6. The 4S is way down here. So on the 4S is what I'm talking about. And so everything up here is just gravy. And you can do a lot. So you can basically just do a lot more of everything. So you've got 6 vibrating strings, distortion, compression, phaser, 5-band parametric EQ, regalia mitra, general excitations for the string, feedback, wah or auto wah, flanger, reverb. That's all going on in real time on a 4S or an iPad 2. And of course, anything later. And you got accelerometers, gyros, touches. You got 5 points of multi-touch on a phone, 10 points on an iPad. That's a lot. You've got X and Y in real time on up to 10 fingers there. And so it's an enormously powerful controller. And the latency is not bad. I find it just fine. A purist may object, but even a real piano has some latency, right? So it's hard to utilize all this. And so we're also coming to Android, but it's got more latency, but it's gotten a lot better. The scheduler is not as good, but we are working on getting onto Android. So here's all the effects. If you run all these effects in real time, or attempt to run them all, then it'll overflow an iPhone 4S, but only by 15%. So you can get all of this stuff going in real time with a 15% overload. So there's that power curve, and here it is with the GPU. So and this also goes to the 6S. So here's the CPU, and then here's the GPU, which is even more strenuously going straight up, following its exponential. So these are powerful devices. Okay, so I will close with a demo of this thing that we're working on. It's an iOS thing. Let me just play Jordan Rudess playing it. There we go.
Hey everybody, this is Jordan Rudess from the band Dream Theater, and I'm very excited to announce to you the release of GeoShred Pro, version 2.5.
So I'll spare you the commercial. So, but what's really exciting to me is that I can do everything I've ever done and more in a phone. That this phone is enough. That's kind of incredible to me that I can do anything I've ever done and more on this thing. And so that's one reason I'm focused right now on actually playing the thing. And I've got one up here if you want to come up during the break and check it out, play it. But I'm out of time, so I better stop here. And that's my update. And the overheads will be a superset of what I just presented because there are links there. And there are more examples, more sound files to listen to. And so you can consider it the online version of this talk. Check us out online.
Thanks very much.
Thank you. Thank you.